Hello, Chem 212 students, and welcome back for the next lecture on acids and bases. So in the last lecture, we described how we could quantitatively compare the strengths of acids and bases using known values of the pKa's and the pKb's. But that doesn't tell us why. It doesn't give us a theoretical understanding of why is it that one acid is stronger than another. And so what we're going to discuss in this lecture is how we can, based on our knowledge of the relative stability of ions, determine what is a stronger acid, what is a stronger base. So this is going to be a qualitative analysis. Previously it was quantitative. We used numbers, pKa's. Now we're going to be qualitative. We're going to compare the structures and structural stability and determine which is a stronger acid. So formal charge is important here. When we did chapter 2, we did a lot of comparing which structures relative to one another will be more stable. And that was based on the positioning of the formal charge a lot of the time. It was also based upon whether a particular structure indicated an octet or not around a carbon, nitrogen, or oxygen. And so we're going to use that same knowledge from the second chapter and apply that to determining the relative stability of acids and bases. So here, which is a stronger acid and why? Well, if we want to know, what we should do is compare the stability of their conjugate bases. So the conjugate base for the chloride ion, after it loses the H+, as we saw in the last lecture, it was that it starts with 3 lone pairs right here and a bond to hydrogen. But then the hydrogen leaves and it leaves its both electrons behind. So you get a negative formal charge. Fortunately, chloride is quite an electronegative atom, and that is important. It means it holds on to its electrons tightly. And that is what we mean when we say that it stabilizes a negative charge. It can keep that negative charge without necessarily reacting and making a bond to anything. Now, that is diametrically opposed here to this alkane. Here, when this bond is broken to the hydrogen, it leaves behind those 2 electrons as a lone pair. And so now there are also 2 hydrogens still attached right here. So that leaves 3 bonds and 1 lone pair on this carbon, which gives it a -1 formal charge. But carbon is not electronegative, very electronegative at all. It does not stabilize a negative charge well. It will definitely react with anything that comes along that's positive and try to fix that. And so we can see that one basis of comparison for our relative stability of atoms with certain formal charges is they depend on the electronegativity. The higher the electronegativity, the greater the stabilization of the negative charge. And so chlorine stabilizes this negative charge far more than carbon. What was another way to stabilize the negative charge in chapter 2? It was resonance, right? Chapter 2 was focused all about resonance. So resonance will be very important too for the stabilization of negative charges in conjugate bases such as these. So we're going to focus on the atom. How electronegative is it? Also of concern will be how big is it? Bigger atoms can stabilize the negative charge better, which is something that we referred to in the second chapter. Resonance will also be important. The greater the number of stable resonance forms, the more stable that ion will be. Induction. So induction is going to be a somewhat new topic. It refers to, we didn't mention it slightly, but it refers to the electron withdrawing effects of very electronegative atoms that are not directly where the ion is, but close by, like on the neighboring carbon. And then the type of orbital where the charge resides. Finally, larger orbitals will be able to stabilize the negative charge better, smaller orbitals where the electrons are closer to the nucleus will be able to stabilize the negative charge better than larger orbitals where the electrons spend more of their time further away from the positive nucleus. And you can remember this, and this is approximately the order of their importance, although there are many exceptions, some of which we'll discuss. This is also the order of the relative importance. Atom is usually the most important, and how electronegative it is or how large it is, then resonance, then induction, then orbital. And you can remember this with the acronym REO, atom, resonance, induction, orbital. So first of all, atom. So the atom, we're talking about the atom that's carrying the charge, and generally a negative charge. And so in attempting to stabilize a negative charge, there are two factors that we want to consider. We want to consider the size of the atom. So if an atom is larger, for example, sulfur being larger than oxygen, it will stabilize a negative charge better than the oxygen will, because it will spread it out, essentially. Spread out that negative charge. So it won't be as attractive to neighboring positive charges. For atoms in the same period, so going left to right, those that are more electronegative will stabilize the negative charge better. And so fluorine will stabilize the negative charge better than oxygen, better than nitrogen, better than carbon. And so you can see here when it comes to propanol, its conjugate base would be one in which the negative charge ends up on the oxygen. And so that would be more stable than that negative charge ending up on the carbon. And if we look back at table 3.1, we will see that that is indeed the case. When we look at the relative stability of acids, we will see that an alcohol, like this one, is much more acidic than an alkane. And the reason behind that is that the oxygen can stabilize the negative charge on the conjugate base much better than the carbon can. Okay, and what about resonance? So resonance is the second important factor, and the more resonance forms there are, and the more the negative charge can be spread out, the less reactive this resulting anion will be as a conjugate base, and so the more stable it will be. Remember, stable means less reactive. And so if we're talking about the conjugate bases of these, for the ethanol here, again, when this bond breaks, these two electrons here will be left behind as a lone pair. So the conjugate base is going to have this oxoanion here. And then for the acetic acid, likewise, also a negative charge will be left behind the lone pair, because again, when the H plus leaves, it leaves those two electrons behind. So you have the negative formal charge here. The difference is that there is no resonance in the conjugate base of the ethanol. However, in this ion here, there is resonance. So we can go like that, and we can get another resonance form, and that resonance form would look like this. And so the fact that these electrons are delocalized and spread out means that when there's a positively charged something coming towards this, these electrons are spread out, and so they're not going to stick and attract as strongly as they would when they are very stuck in one spot. So this one spot is very negative. So if something comes along that is positive-ish, it will definitely react with this very easily. However, this one, the negative charge is spread out over a larger area. I always like to compare it to magnetism. There are some parallels between magnetism and electrical charge. They actually are kind of two sides of the same coin. But without going into too much detail, I like to think of like the magnet that you put on your fridge. You might have a small one that sticks really well, and that might have the same overall magnetic attractive force, but it's all concentrated in a small part, so that sticking to your fridge is much stronger than if you spread out that magnetic attraction on this big like pizza box magnet, like the ones like the size of a card. That one might not hold your piece of paper up because on the fridge, because it might not stick hard enough, because that magnetic attraction is spread out over too large of an area. There's a similar analogy here with negative charges. When the negative charge is stuck in one spot, it's very sticky. It will stick to something positive and go and react. That makes it less stable, more reactive. Whereas when you have a resonance structure, that negative charge is spread out. And so it's like the pizza box magnet, where it just doesn't it doesn't stick as well, because that attraction is spread out over a larger range. So it's not quite as reactive as something like this. And we can again look at the pKa values. So let's compare. We say ethanol must be a weaker acid than acetic acid because its conjugate base is less stable, so it will go back to ethanol more easily. And so we would expect the pKa for ethanol to be larger because it's a weaker acid, and the pKa for acetic acid to be smaller. It's a stronger acid. And indeed, if we go back and look at the quantitative values here, we can see that indeed a carboxylic acid like acetic acid or ethanoic acid is much more acidic than ethanol alcohol. Okay, so that's the resonance portion. Induction. So induction can also stabilize a formal charge by spreading it out a little more. The way in which it's spread out, it's a different type of mechanism, the way in which it happens. Essentially, it's drawing electrons through the bonds in neighboring atoms. So when you have more electron withdrawing groups, meaning attachments like these chlorine atoms that are high in electronegativity, they really pull on electrons. This is going to pull electrons away from the region that has the high electron density and spread out that negative charge even more. And so what you can see here is we have acetic acid, which has a pKa of 4.75, but if we add a chlorine on the atom next to this carbon, okay, so the negative charge is in here, right, in this resonance form, this carbon is one carbon away. Inductive effects do get much weaker with going one more carbon away. And then after another carbon, they're almost negligible. So they essentially got to be one carbon away to have a really powerful effect. And you can see this effect is quite powerful here. If we add one chlorine atom, it's withdrawing electrons towards itself. So it's drawing electrons this way, which is away from the region of the delocalized negative charge. You add another chlorine, this effect is increased, and a third chlorine will increase it even further, making the acid more and more acidic the more electron withdrawing groups there are. Be careful with this. Always think of how close the electron withdrawing groups are to where the negative charge is, because when they get even one more carbon away, this effect is much more reduced. Finally, orbital. Orbital is the last factor. And when we have the negative charge occupying a hybridized bonding orbital, it will be more stable, that negative charge, if it is held closely to the nucleus, because the nucleus is positive, so that's what's attracting the electrons. So if that negative charge, formal charge, is in one of these smaller sp hybridized orbitals, which is smaller because it has less p and more s characters. So the s is spherical and smaller. The p is dumbbell shaped and more spread out. So the having these electrons in an sp orbital is more stable than having them in an sp2, and more stable than having them in an sp3. And the reason being is because those electrons will be closer to the nucleus, and so they'll be held on to more tightly, which stabilizes these charges. So here's an example with the acidity of ethane, ethene, and ethine. Also, these are, ethene is commonly known as ethylene, and acetylene has ethine has the common name acetylene. But we can see that the acetylene, which is sp2 hybridized, so this carbon has X equals 2 bonded atoms, E equals 0, X plus E is 2, so this is sp hybridized. And then this one here is X is 3, E is 0. It is sp2 hybridized. 3 bonded atoms, no lone pairs, sp2 hybridized. Here, 4 bonded atoms, no lone pairs. X is 4, E is 0. So here X plus E is 4. So it's sp3 hybridized. And so you can see that the acid which would have a negative charge on its conjugate base. So if this H plus was removed, you get the conjugate base. That, and this negative formal charge will be better stabilized in the sp orbital than in the sp2, and better than in the sp3. And so the pKa will be lower. The acetylene is a stronger acid because its conjugate base has a more stabilized negative charge. So if a strong base were to react with the following molecule, it would have to be a very strong base, because this is alkanes and alkenes and alkynes are terrible acids. But which would be the most acidic proton here? And well, when we look over here, we're thinking, okay, if we have a hydrogen that's on sp hybridized carbon, that would be the most acidic hydrogen. However, there are no hydrogens attached right here. This carbon is making 3 bonds to another carbon and 1 bond to another. So it's already making 4 bonds. There's no hydrogen. Same for this carbon here. 1 bond to this carbon and 3 to the other. It's already making 4 bonds. No hydrogen. This carbon here is making 4 bonds as well. 2 here, 3, 4 altogether. But this carbon is making 2 bonds to this carbon and 1 bond to this. So it does have a hydrogen. And that hydrogen is attached to an sp2 hybridized carbon, so it would be more acidic than any of the rest of these hydrogens which are attached to sp3 carbons with no double bond, no triple bond. A very strong base would be required because, again, if you look at these pKa's, the pKa for this will be around 44. It's super high. These are not acidic at all. You'd need a super strong base to pull this H plus off. So when we assess the acidity of protons, we're going to use this REO as the order of priority. So atom will be generally the most important, then resonance, then induction, then orbital. So for example, if we compare the relative acidities to these, the ethanol is much more acidic than the propylene. And the reason why is because if we look at the conjugate base here, the conjugate base would be this oxygen, and it would have, it's got 2 lone pairs right now. It would have 3 after the H plus leaves, because again, these 2 electrons here will be left behind. So we'll have a -1 formal charge. So here the formal charge, the negative formal charge, is on an oxygen atom. And so that's really important. That's our #1 order of priority. Here we have a propylene. So if the, and notice there's 2 more hydrogens here which aren't drawn. There's 3 hydrogens attached here. And so if this hydrogen leaves, it leaves behind a lone pair, and we have a -1 formal charge here. But this does have resonance structures, right? We can draw a resonance structure for this because we have an allylic lone pair. So we need 2 arrows for this one. Hopefully you remember from chapter 2. We can draw another resonance structure here, and we get, oh, I'm going to go behind my head, so I'll go above my head here. And we get now that we have now the lone pair is over here, the negative charge is here, and we have a double bond here. However, resonance is the second most important, and you can see it's quite a difference in importance. The fact that this negative formal charge is on an oxygen really stabilizes that negative charge relative to it being on a carbon. Even though there's resonance structures, it doesn't really have as nearly as the impact as having that negative charge on a very electronegative atom here. Now, it's important to realize that REO is a useful rule of thumb, but it's not foolproof. If you really want to know how stable an ion is, that actually involves either an experiment in which you observe the relative stabilities of this by looking at maybe the equilibrium in a reaction and how much product there is relative to reactant. Because remember, we talked about in the last lecture, these reactions will always go from the weaker acid and base to the stronger acid and base, or generally from the less stable reactants to the more stable products, right? Whether that's going forward or backwards in that equilibrium. So we can observe this, or we can do a quantum mechanical calculation. That would be determining the relative stabilities more exactly. However, this is a very good rule of thumb, even though it doesn't always work. Here's a perfect example of that. If we're using REO and we want to decide which of these would be the stronger acid, okay? Well, again, we look at what the conjugate base would be. Here, if the H plus is removed, that leaves the lone pair here on the carbon. And so that's the conjugate base here. If ammonia behaves as an acid, it loses an H, that leaves behind a lone pair. It already had one, and then it has two H's attached. Okay. And so this nitrogen has a -1 formal charge. So if we were using REO, we'd say, well, the negative formal charge on the conjugate base of ammonia is on a nitrogen atom, which is more electronegative than a carbon atom. However, the acetylene is actually the stronger acid compared to the ammonia. The ammonia is actually more basic than it is acidic. Why? It's because there are other factors that aren't as easily worked into this REO system. And that factor is that the ammonia can accept a proton. If it accepts a proton, then it has 4 bonds to hydrogen now. And the lone pair was used to make the bond. So it has a +1 formal charge. And indeed, ammonia can accept protons in this way. And so that's this competing reaction that's going on, which results in this, this deviation from this simple REO system that we're using. So if you want to be absolutely certain, you should go and look at the quantitative experimental data. But the REO is often a good rule of thumb. A good thing for you to do while you're doing these homework problems is to make your prediction, then go look at the relative pKa's and see. At least you won't see the exact molecule, but you'll see sections of the molecule that can help you to approximate it. And you'll see if you're right or not. So here's an example. And so this example shows us going from this stronger acid, relatively speaking. So here we have the conjugate base of ammonia. So here's one of our acids. It's the ethyne, or acetylene. And here's the other acid that we wanted to compare, ammonia. And so remember, the reaction is going to go from the stronger acid to the weaker acid. Okay, so here's the conjugate base of the ammonia. Just as we drew last time, it has 2 lone pairs and 2 bonds, a negative formal charge. And here is the conjugate base. So let's just label them real quick. This is the acid for this reaction, and this is its conjugate base. And on the other side, we have our other acid that we're comparing. So this is the acid, and this is its conjugate base. And here, if we compare the pKa's, we see that the pKa of the acetylene is lower than that of the ammonia. Therefore, this reaction is going to go from the stronger acid to the weaker acid. Relatively speaking, we can say things about the bases too. This would be the stronger base relative to this base here. This would be the weaker base. Why? Because the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. So this reaction is going to go from stronger acid and base to weaker acid and base. It's going to go very strongly to the right. Okay, so here we have a question where we're based on REO. meant to indicate the relative stabilities of each of these acids, these protons here. So we got one labeled HA, HB, HC, HD here, and HA, HB, and HC. Okay. All right, well, let's compare these now. So first, we're going to focus on atom. So atom, right? ARIO, atom resonance induction orbital. Okay. And so in terms of atom, the HA and HB and the HC are all connected to a carbon atom. So the most acidic of these protons is going to be the HD. The most acidic is going to be the HD. So I'll see it in terms of acidity. HD is the greatest. It's the most because of atom. Okay. So now we're done with atom. We're going to move on to resonance. And we're done with atom because that was the only one attached to oxygen. The rest are attached to carbon. And so now let's move to resonance. So in terms of resonance, let's think about what the negative ions would be. If this H plus goes away, it goes away, there's going to be a negative, a lone pair here putting a negative formal charge on this carbon. If this one goes away, there would be a negative formal charge here on this carbon. And if this one goes away, there will be a lone pair here and a negative formal charge on this carbon atom. So in terms of resonance, this one has a lone pair, allylic, an allylic lone pair. So it has resonance. The resonance would look like this. It would be this lone pair makes a double bond. This one goes. And so because this one has resonance and the others do not, it would be the next most acidic H plus ion. So HC. Now, neither of these HA or HB, neither of their conjugate bases would have resonance. So we move forward to induction. Now with induction, here we have a fluorine atoms that are a little ways away. Okay, it's attached to this carbon, which is right next to this one. And so the HB has an inductive effect here that the HA does not. And so the HB would be the next the next most acidic proton. Finally, orbital is last, and this is in an sp2 orbital. However, that is the least important of the factors, and so that is the result there. All right. Next, let's take a look at this one. So for HA, again, we go to atom first. Atom. So in terms of atom, oops, I just realized I made a mistake on this one. I do have to take a closer look because in my induction, or in my resonance, I forgot to notice that in my resonance structure, this negative formal charge can actually end up on the oxygen. So I made a mistake there. Sorry about that, guys. Let's fix that. So when it comes to the atom, you also have to look if there's resonance. Will that formal charge be able to end up on a favorable atom? And I neglected to notice at the beginning that this negative formal charge due to the resonance can result in the negative formal charge going onto the oxygen atom. So here it will actually be that the HC is greater in acidity than the HD, because not only can the negative formal charge go on an oxygen atom, which is favorable, it's more electronegative, there is resonance, so there's both. And so that was my mistake there. I've neglected to notice that when I'm drawing it. I jumped to atom right away. But it's important to notice the resonance structures there. And so this resonance structure does allow for the negative formal charge to go on an oxygen atom here too. All right. Okay. And I'm looking at the inductive effect now too. Geez, I made 2 mistakes. Oh well. This goes to show you that even your professors can make some mistakes. This isn't so bad. Something I noticed too is it was something that I warned you about earlier. When I'm looking here, the inductive effect is strongest when you're 1 carbon away. So this inductive effect would be strong if this lone pair were in the 1 carbon away from the fluorine. However, it's 2 carbons away. So that was my mistake there. At that point, we don't have a very strong inductive effect. And so the orbital in REO, remember REO. So induction, I miscounted my carbons. I thought it was 1 carbon away. It's actually 2. So what I want to do is notice that this inductive effect won't be so strong. So I go over now to orbital. And this one will be HA then will be stronger than H. Okay, there we go. All fixed up. Sorry about that. All right, now let's take a look at these other ones here. So again, we're going to use REO. I'm going to say atom first. And this time I'm going to look carefully at my resonance structures, right? Don't want to make the same mistake twice. So let's take a look at what would happen here. If this proton leaves, it leaves behind this lone pair. So this bond won't be there anymore. There'll be a lone pair, and there'll be a negative formal charge because there's already a lone pair there as well. That wasn't drawn. Now, this is not an allylic lone pair. This is a vinyl lone pair. So there's not going to be resonance here. Okay. Now let's look at what possible resonance structures here. If this H plus goes away, it's also going to leave, there's 1 lone pair right now because nitrogen is making 3 bonds with 1 lone pair. There'll be a second lone pair now. So there will be a negative formal charge on this nitrogen. And this, in fact, does have resonance structures. Those resonance, because this lone pair is allylic. However, if let's see, and so we have there's quite a few resonance structures. I don't want to draw them all, but essentially you'd have this making a double bond here, and then this goes. I'm just going to do the kind of the quickie version. This goes here, this goes here, right? And then we have a double bond here, and so at that point we have an allylic lone pair, and so we can have some resonance here with the oxygen atom. However, that resonance would involve the oxygen with a positive formal charge, and so that would not be favorable. What is favorable here is that if this H plus leaves, we have a negative formal charge on the oxygen because it has 2 lone pairs, and now when this leaves, it'll have a 3rd lone pair, and so it will have a -1 formal charge. And so in terms of ARIA, let's see, we have a negative formal charge on the more favorable oxygen atom. However, the height, and so let's now compare them. Okay, so when it comes to the relative stability, we do atom first, and this one also has resonance. Notice this is also an allylic lone pair, so it will have its own resonance. So it's got atom and resonance. So HA is going to be the greatest in terms of acidity. Next, we'll look here, and we see that we have this one here, which does not have resonance because it's a vinyl lone pair. So they're both nitrogen, but the HB has the the resonance here, right? And the HC does not. And so the HC would be the least acidic. And so this is how we can compare the relative acidity of protons on the same molecule, as well as relative between other different molecules. So sometimes acids will have a positive formal charge. We've seen this in a couple of the examples on the on the pKa table. When they have a positive formal charge, their conjugate bases will be neutral. And we can use REO to compare the stability of acids when they're neutral as well, and see which is best at stabilizing the positive formal charge. So, for example, here, ranking these acids in terms of strength, which would be able to stabilize the positive charge the best. Okay. So here, if we look, let's see here. Generally, oxygen is pretty bad at stabilizing a positive formal charge. It wants to actually have electrons around it, right? It's very electronegative. So we can compare that relative stability of stabilizing the positive formal charge here, and we can see that the nitrogen here will stabilize the positive formal charge better than the oxygen. And so these are going to be the ones here that have the higher stability the way they are, meaning they will be less acidic. Okay, they're stable the way they are, meaning they will not react as well as an acid. Okay, and when they do, let's write what they get when they do behave as an acid. So this oxygen, for example, here has 1 lone pair and 3 bonds. If it behaves as an acid, that H plus will be removed, and these electrons will be left behind right here. And so we'll have an oxygen with 2 bonds and 2 lone pairs. That will be that one there. Same thing here. This one has 1 lone pair. Okay, it will then have, once the H plus leaves and these electrons are left behind here, it will have 2 bonds, and so these are the conjugate bases of these acids. Here we have a nitrogen atom, 4 bonds, no lone pairs. When the H plus leaves, it again leaves behind these 2 electrons, and so now this nitrogen has 3 bonds and 1 lone pair. This oxygen here, again, if it loses this plus, it's got 2 bonds and 2 lone pairs. And finally, this nitrogen here, again, these electrons will become a lone pair. And I make sure I don't write behind my head here. Right? So there'll be 1 lone pair now and 3. So now let's compare. So really, we're going to compare the relative stability of these ions here. And again, in this case, what we're saying is that the acid here, if it's stable, it's going to be less acidic because it's stable just the way it is, right? So in terms of stability, we've already said that, and so in terms of greater acidity, okay, the least acidic is going to be the ones with the nitrogen. Now you can see here that structure, so that leaves us this structure here and this structure here. Okay, so in terms of the relative stabilities of these structures. We've got electron withdrawing groups here. So we do have an inductive effect. Notice that here it's one away, right? It's one carbon away. And so this will be significant. And then we have no inductive effect here for the nitrogen. Okay, and then now the rest of these we have oxygen. So let's take a look at the oxygen. Okay, here we have a positive formal charge that is allylic to this oxygen, allylic to this positive formal charge, that where the oxygen has a positive formal charge. And so a possible resonance move that we have here is that this can go over here, and the result would be that this carbon after that would have a positive formal charge. It would have 3 bonds and no lone pairs. So there is some possibility for resonance there, right? In terms of this one here, there's not that possibility. Neither is there here. So in terms of the stability of this ion, this increases the stability of this ion due to resonance. And so this one here, being that it's oxygen, this one's going to be the most acidic. The most acidic. And so it says increasing acidic strength. So I'll put this on the right. So increasing acidity. All right. So this one right here, I'm gonna label these A, B, C, D. So A, B, C, D. So the structure here that I'm calling D, this one is going to be it's going to be the most acidic. Next, we'll have B here being the next acidic. Then we're going to have A here being next in terms of acidity. And these are all more acidic than the ones that contain nitrogen. Because again, the oxygen cannot stabilize the positive formal charge as well as the nitrogen can. Okay. All right. And let's think about it this way too. So here what we have is we have a orbital situation, right? The positive formal charge is on this oxygen, which has 3 bonds and one lone pair. It's sp2 hybridized. Okay, and so it can then it would stabilize a negative formal charge greater. However, this is a positive formal charge. Okay, the opposite of that. And so we're going in the opposite direction there. The B is right in the middle, and then the oxygen here is allylic to a form to a lone pair here. All right. Finally, for the nitrogens. Here, we've got this electron withdrawing effect here that doesn't exist in the nitrogen there. And so in terms of the stability, it's going to be letter E here, letter E, due to this electron withdrawing effect, and then finally this C, which does not have it. And so this is the order from least the least acidic to the greatest, E being here the greatest acidity, the least stable of these positive formal charges. Here's another practice problem, and this one has to do with the relative stability of bases. Okay, and so just the same way we can do the relative stability of acids, we can do the relative stability of these bases here. And so let's take a look at the bases. Remember, a stabilized negative formal charge will mean that this is less basic. Will mean that it's less basic, right? So let's compare these real quick. All right. So we're going to use ARIO. We're going to compare the relative stability of the negative formal charges. All right. So let's take a look here at, we've got these labeled A, B, C, D, and E. First of all, let's separate them into kind of two groups. So notice that in B, D, and E, the negative formal charge is on a carbon atom, which is less stable and less favorable compared to having a formal charge on an oxygen or a nitrogen atom. Okay. Now B is going to be here the strongest of these bases. And why is that? Well, here the the negative formal charge is stabilized by this electron withdrawing effect from the fluorine. That is also the case here. However, it's also a vinyl in an sp2 hybridized carbon. So in terms of the strongest base is going to be B. So this is going to be, I'm going to order these like this. Oops. Your strongest base, weakest base. And the strongest base is going to be the one that has the least stabilized negative formal charge on the carbon. It's going to be B. So that's going to be the strongest base. Next, after that, we have a negative formal charge on an sp3 hybridized carbon. So this is sp3 hybridized. And this one's sp2 because of the double bond. So this is sp2. This one here is sp3. And so again, the negative formal charge will not be as well stabilized here on the sp3 carbon as it is on the sp2. So D is going to be the next strongest base. Finally, E. And that takes care of all of the ones that have the negative formal charge on the carbon. Okay. Next, we have this one with the nitrogen, this one with the oxygen. As we have seen before, the nitrogen ones don't work very well with ARIA, right? ARIO rather. The reason being, the nitrogen atom is significantly basic. It can make a bond with a hydrogen atom here. When we can think about the conjugate acids and their charges. So here, and that works fairly well with ARIO. So here, if this oxygen makes a bond to a hydrogen, an H+, now it will have a positive formal charge of positive, and that will be a hydrogen. For this one, this nitrogen, I'll draw that one right here. Kind of I ran myself out of space a little bit, but if I draw the conjugate acid here, it would have 4 bonds. 2 of those are to carbon, 2 are to hydrogen. It would have a positive 1 formal charge. So in terms of stabilizing that charge here, neither of these situations would be particularly good. But as we were saying before, we had this example before. This is a little bit where ARIO kind of fails. It's with the nitrogen atom. In this particular case, it can behave as a base. So letter C is going to be the next strongest base. And then finally, it will be the least strongest base, the weakest is. And so that wraps up predicting the relative stabilities of acids and bases using ARIO. This is something that takes a lot of practice, and there's a lot of pitfalls. Like you even saw me with the first one comparing the hydrogens. I neglected to notice a resonance structure where the negative charge could be stabilized on the oxygen. And so this is something that you're going to want to practice a lot, get better and better at. and it will be very important for predicting what are going to be the directions of our mechanisms and the way in which reactions will occur moving forward. So that's going to be the end of this second lecture. For the last one, we're going to focus on predicting the equilibrium position of reactions based on the relative strengths of acids and bases. And so I'll see you in the next one.